Very good morning, everyone, and thank you for joining us bright and early on this session where I want to take a bit of a tour through some electrical myths and things that we commonly encounter in training courses. Now, there's no particular order to today's session, and it's questions are very much welcomed as well. So if we do a quick bit of housekeeping first, you have the ability to do questions via the chat. So there's one already in, and we have some questions that have already been pre-registered as well, some of which I will actually be answering as we go through. But please do chip in as we go, and I'll try and keep an eye on them and cover them as we go along. If not, I'll do them when we get to the end. So I do have one. Any idea why full screen is not available? Now that is a question for you, I'm afraid. Jamie, you there? Is that something you can help with? Oh well, hopefully something will come up with that. So excuse the holding slide. Of course, this is not a Zoom session, so you don't need to leave your mics off because you can't talk. But like I say, please do be interactive and ask questions. You know, they're very welcome, and I'll try and go through them in as many as we can in the hour that we've got. So if we go to the first slide, just a quick brief bit about me for those who don't know. I've been involved in theatre, touring and events for many years, with the old forays into film and TV as well, and broadcast. And through my work with Plaza and other associations like the ABTT, I sit on standards committees, and through that's led to writing of books on electrical safety and recently the IT's Code of Practice on in-service inspection and testing, formerly known as PAT testing. And we do training and also do consultancy, currently working on the Commonwealth Games, which is coming to Birmingham next year. So that'll be an exciting shot in the arm for the industry, I hope. So the key thing is very much feet in the industry, and but also have a good appreciation of electrical safety requirements and management. So if we go on to our first intro slide, what I want to do is cover a couple of things, and I've broadly categorized the subjects into electrical theory ones, like phase separation is one that's been questioned already, and electrical safety management myths. And I want to try and explore some of these and put a bit of context around them. You know, I thought it'd be quite fun to do something a little bit more interesting rather than just concentrate on the specific subject. So if we go to the next slide, we'll start with a couple of theory ones. Now, one of the perennial things I still come across, particularly on training, is people insisting that you coil cables in a figure of 8. And when you ask them why, there's usually some sort of hazy answer about how it cancels out the magnetic fields, it stops it overheating, and similar. Well, as we'll see in the next slide, that's not the case. If you imagine you've got a coil of cable, and forgive me if electrical theory is not your thing, bear with us a sec. If you imagine you've got a load connected to our extension lead that's coiled up, that load draws current. So if you're looking at the plug in the picture, current is going to flow down through the live pin, through the brown wire, all the way through the socket, through the load, and then back down the neutral again. So if our load is drawing, say, 10 amps, for example, we'd have 10 amps flowing through the live, but would also have 10 amps flowing back down the neutral. Now, what we do know is that when current flows through a wire, you set up a magnetic field around it. So the current flowing through the live is flowing in one direction, so the magnetic field is of one polarity, but the current flowing down the neutral is in the opposite direction. So the polarity of the magnetic field is in the opposite sense, and the two cancel each other out. So there is no residual magnetic field in a coil of wire. So coiling extension leads and sockets in figure of 8 is neat and looks pretty, but it doesn't actually provide any electrical benefit to the system. So if we go to the next slide, what we'll see is the reason why cables get hot is because they can't dissipate heat. Now, if you are a bit savvy with electrical theory, you'll know that current flowing through a resistance will give rise to a voltage drop, and that manifests itself as heat. So if you look at the equation, power is the product of I squared times R, then if our cable has resistance and it's got current flowing through it, it'll dissipate power, and that's why cables get warm. So a good example is a pile of cable on a fly floor, or as you can see in the picture on the right, dimmer city, or just a cable coiled up on a drum with a load on it. And you can easily demonstrate this to yourself at home. Just plug the kettle in or a fan heater into a coiled up cable. Then after 5 minutes, unwind it and the center will be really hot. And the reason for that is because with the current flowing through the resistance, it dissipates power. In the center of the drum, because the cable is all covered by more cable, it can't dissipate that heat. And so it gets hot. And so if the conductor heats up, how did that happen? That was good. I managed to mute myself without touching anything. So as I say, so if you've got current flowing through the resistance, the cable will heat up. And if it's insulated by other cable on top, it can't dissipate its power. And so it makes the resistance increase because it gets hot. So the resistance of the conductor goes up. And that leads to a thermal runaway. And that's why cable drums melt. And sometimes you can find even cables at the side of the stage where you've got dropping down off a truss, for example, and they're all heaped up in a pile at the bottom. When you stick your hand in the bottom of that pile at the end of the show, it can be really quite hot. And the idea really with cables is to pay them out, and long loops get as much exposure to air so that they can naturally dissipate their heat to stop them getting too hot. So that's how electrical fires start, principally, is current flowing through a resistance, which causes that heat, which is a self-fulfilling or in danger of being a self-fulfilling prophecy and just overheating and catching fire. So that's that. Next slide. Audio should be on its own phase. Now, there's been a couple of related questions to this as well. So phase separation is, and audio being on separate phases, are a little bit aligned, but there's different strands to this. So we'll try and cover a couple of them. Now, again, it's here, it's a myth, it's not true. So if we go to the next slide, I'll explain why. So I'm just checking the chat. I'll come back to some of those. In terms of hum signal degradation in whether it's lighting or DMX or video or audio, it's very rarely because of bad quality mains waveforms. You know, manufacturers, particularly of audio kit, spend a lot of money developing very quiet, low noise power supplies so that you don't get any artifacts from the mains appearing on the output of their expensive mixing desks. So for the most part, interference always stems around earthing arrangements. And that is to some degree interlinked with what phase you're on. And that's where the confusion stems from. So if we go to the next slide, a little bit of electrical theory here on three phase. What we have on the right-hand side is an example of a three-phase system. So we've got 3 coils of wire, and the 3 white boxes in the bottom right of the left-hand image denote the loads. Now, if these loads are all equal, we have an equal current flowing in each phase. So if you imagine current coming out phase 1, you've got I1 flowing out of the winding, down through the load, and in a balanced system, that current actually flows back down loads 2 and 3. So no current goes down the neutral in a balanced 3-phase system. And for that reason, you probably noticed motors, chain hoists, and similar only have a 4-pole connector, because you have the 3 phases and the protective conductor on the earth, because it's a balanced load. It doesn't need a neutral. So in other words, if you put all your audio on one phase, you're still going to get all the dirty lighting currents and everything anyway. So it doesn't make any difference being on a separate phase. And for electrical safety reasons, you're better off balancing the phases out and making sure you have equal loads on each phase. Just quickly on the graph on the right, it's not very well drawn, and forgive me for that, but at time t, what you can see is you've got the red, green, and purple phase currents, and at time t, the purple phase has got an equal and opposite current to the sum of the green and red phases. So in a balanced system, at any point in the voltage waveforms, all 3 currents add up to 0. So that's a key feature of a balanced three-phase distribution. So if we go to the next slide, I'll explain a bit about where the noise comes from. Now, if you have a difference in earthing potentials, we get currents flowing down screens. So a good example would be a theatre. You have possibly your own substation coming into a big distribution board. Then you have some fairly substantial supplies going to the stage, because that's where a lot of the power gets used. Then you might have another supply coming from that original distribution board, maybe via some other distribution boards, all the way to the front of house position. Now, imagine we have amplifiers plugged in on the stage, connected to the stage distribution. We have our front of house mixing desk plugged into our front of house position, plugged into a socket locally up there. In an electrical system, a lot of electrical equipment, particularly switch mode power supplies, laptops, etc., leak a little bit of current as a feature of the filtering. So that means that we'll have, generally throughout the distribution, a little bit of current flowing down protective conductors. Now, again, going back to Ohm's law, if you have current flowing through a resistance, you get a voltage drop. And so what we can end up with is the earthing arrangements at the stage at a very slightly different potential to the front of house position. So long you come with an XLR, connect your mixing desk to your amplifier, and you've effectively just shorted out the electrical earthing. And so that can then lead to currents flowing down the screen. And if you get current flowing down the screen, that can lead to interference. So it really does manifest itself when you have a difference in earthing potentials. Now, this leads on to the subject of clean earths. And in older theatres and some studios, you might come across technical earths or technical supplies which are specific typically to the audio crew. And the original design of those systems was to have a very separate supply at the origin, a separate distribution going throughout the building. And that would be dedicated for audio use, for example. And there was a good example of a studio, I think it was at South Bank, where they deployed this and they put expensive monitoring in, so that if someone breached it by, let's say, plugging in your lighting desk into one of the audio sockets, it would sound an alarm. But of course, the alarms were going off all the time and they couldn't do anything about it. So they eventually just turned the whole system off. Technical earths and clean supplies are very, very hard to police, because a really innocent example, like I say, plugging a signal cable from your lighting desk to your mixing desk, if you're running timecode or similar, effectively could short the two systems together. So because it's so hard to police, they're not recommended. For some time now, the wiring regulations in Part 4 has suggested that you create a big earthed mesh network. So you bond all of the supplies to any bits of structural steelwork you can find, so that in the building, from one end of the building to the other, it's very hard to get a potential difference to occur. And so on that basis, you get less interference. So technical earths and technical supplies is something that's long been not recommended for production venues. So thank you to Simon and Adam for that question. Similarly, phase separation. Should you keep 6 feet between phases? Again, that died a death in the wiring regulations with the 14th edition. So we're talking late 50s, 60s time, and yet its legacy still persists. When that regulation existed many, many years ago, electrical safety wasn't anything like we have today. And we relied on fuses. We didn't have test equipment, so we couldn't test circuits. We only had continuity testers. We couldn't do loop checks, for example. And so it was foreseeable that you could have a fault on one phase and a fault on an appliance on another phase, and be in simultaneous contact with them both. Now, electrical safety over the years has obviously got a lot better, and the chances of that happening are very slim to almost negligible. Added to that is the fact that we also now know through other research that getting a 400 volt shock isn't much worse than getting a 230 volt one. So the key driver in electrical safety is just don't get the shock in the first place. So if we limit the chance of an electric shock, then the chance of being able to touch two bits of kit on different phases, both under fault conditions and live when you happen to be simultaneously touching them, is in a properly designed and set up system is very, very unlikely. So that's like I say, something I still find now. People say you can't have more than one phase in the same rack, or you can't have more than one phase up the socket pecs, for example. As long as the equipment is designed for ordinary mains voltage, it should be able to withstand 400 volts. So there's no need for phase separation. And again, just to finish off on phase balancing, one of the other questions, yes, very important to keep phases balanced. Make sure you've got equal loads on each one. So splitting audio up onto its own phase, very much a no-no. So make sure you distribute as much of the load as you can. Just quickly, if you lose the neutral and you've got all your audio kit on one phase, and neutral failures do happen, the chances are, being the lightest loaded phase, you'll be the one with the largest voltage swing and all your kit will blow up. So it's a very good idea to make sure that in a three-phase system, you balance loads as much as possible, whether it be in a building or on a festival stage running off a generator. The theory is very much the same. So I think, why is phase separation still so common in theatre and demanded of by venues? Is it a misunderstanding of regulations or poor training? It's legend almost. Like I say, it died a death 40 plus years ago. So it's still one of those bits of folklore that gets handed down. And when someone says that and you're reading some lights, they say, oh no, you can't have them together, because if you get a fault, you might have a 400 volt shock or similar. And when you think about it, you think, oh yeah, that doesn't sound unplausible. But when you look at the safety requirements, it's a non-starter. So very much good practice to have separation between them. On an allied one from Craig, is it still good practice to have separation between power and signal, i.e. video and audio cables? Or is this less important with improved cable insulation? Well, it's still recommended that you keep separation, because you can still get radiated magnetic interference emanating from cables being induced on signal cables. Although, given the quality of balance lines and receivers these days, it's much reduced compared to what it used to be. That said, you still do get, and I've had installations where we've had DMX receivers that are non-compliant, so we've managed to form earth loops and similar, and that is much more susceptible to interference. So it's a good idea to keep it separated. But from an electrical safety aspect, you can run cables in the same enclosure altogether, but the insulation of all the cables has to be rated for the highest voltage present. So if you're running mains and audio together, the insulation on the audio cable should be rated for 400 volts, for example, or more, to make sure that if there is a fault, then the audio cable is going to be suitably protected. And of course, it's quite common now to have composite cables for front house looms or lighting trusses where you've got power and data running the same cable. Absolutely fine, like I say, as long as the insulation for the signal cables is rated accordingly, so that you don't end up with any risk of mains voltages being imported onto the data cables in the event of a cable fault, for example. So hopefully that answers that one. Okay, fine. So I think that's it for the questions on that for a sec. So if we move on to the next one. Low voltage battery equipment and LED lighting is safe, no risk of shock. Let's go down the battery route. True up to a fashion, as we'll see in the next slide. With the electricity at work regulations, which govern electrical safety in the UK, they don't have any voltage limits. And it doesn't say that these regulations only apply to voltages over 50 or don't apply over 1,000 volts, for example. They apply in all situations. And the reason for that is because electricity is a source of energy. And electric shock is not the only hazard that can manifest itself in electrical systems. So batteries in LED uplighters, phones, etc. You've probably heard of horror stories of people having their phone on charge on their bed and there's a fault in the battery and the bed catches fire. Now, even a radio mic with a faulty rechargeable battery sitting in its cradle could potentially overheat. I've seen power over Ethernet phones melted through faults, similar faults as well. But in respect to the regulations, because that fire can cause injury, it starts a fire, people could suffer smoke inhalation or be trapped in a burning building and regrettably die. the risk of injury is present. And so therefore, the electricity at work regulations very much applies to any voltage source where the energy level could give rise to the risk of injury. And given that even very small battery stored energy systems can give rise to a degree of fire, it stands to reason, therefore, that there's no voltage limit in the regulations themselves. Just on that subject, actually, power over Ethernet is getting much more common now, as we see a lot of networked equipment run on power straight from the network switch itself, which is great, saves power cabling running around the place. But of course, it's a fairly high power rating. You know, you can get 10s, 40 plus watts down a PoE network cable. Now, that's fine, but of course, again, there's still a risk of fire. If a cable is damaged, it can overheat. That overheating can then lead to the, as we saw earlier, the self-fulfilling cycle of melting, potentially catching fire to something. And for that reason, we can potentially expect to see power over Ethernet systems coming into the wiring regulations in the future. Something that's being worked on internationally in Europe at the moment. So will eventually be embodied in BS 7671, the wiring regulations in the UK. And it's for that very reason that although the shock risk is very low, the fire risk is still very much present. And even though low voltages generally, you're not much at risk of a shock, they can still kill. And you know, an example was a case where a guy was doing some arc welding, and arc welding is quite a low voltage, but he was lying on the workpiece and he took the rod out of his hand because he had good body contact and was quite sweaty. There was enough current to actually kill him. So low voltages under the right conditions can actually kill as well, although statistically, and looking at body, you know, typical body impedances, it's unlikely, but possible. So I think that's that for that one. So if we go to the next slide. Tents and towers should be earth. Again, this is a common theme that I find on training courses. We talk about electrical safety, protective bonding, and people often say, well, we put an earth rod down at the front of a house tower. And when asked why, they say, well, for electrical safety. And is it for lightning protection, or is it protective bonding to limit the voltage differences in the tower if a fault occurs? And you start scratching beneath the surface a little bit, and no one is really sure why this happens. I know some tent companies do it religiously, put earth electrodes down on and connect them to their structures. But why? Why would we want to do that? So if we go to the next slide, what we tend to find is that for electrical safety, for creating an equipotential zone, which is the whole point of protective bonding, and for the less technical amongst you, you might, if you have old copper plumbing in your house or your flat, when you look at the kitchen sink, you might see green and yellow wires connecting the pipework together. The reason for that is to limit the chance of a potential difference occurring in the installation. So if you've got your hand on your earthy metal sink because it's connected to the cold water main coming into the house, and you grab your faulty kettle, if I join the casing of the kettle to the sink, then I short the two out. So there's no voltage difference that can occur. So I limit the chance of me getting a shock from hand to hand accordingly. So that's the basic principle behind equipotential bonding. So we have a similar situation, let's say, in our front of house tower. So we've got a guy with a follow spot on the top leaning up against the railings. If the tower's sitting in the wet mud, the tower's at earth potential. So if there's a fault on the follow spot, we want to limit the chance of bad shock between the person, the follow spot op's hands, and their bum when they're leaning up against the scaffolds behind them. So if we join the two together, we create that equipotential zone. Trying to do that by putting an earth rod in at the tower and expecting that to find a reliable path back to the earth rod at the generator is more likely to be more hazardous than doing nothing at all. So for electrical safety, you need to think about actually connecting the tower properly to the earthing arrangements of the supply coming up. And so a good example of doing that is just to take a supply, a protective conductor connection off the distro that's powering the tower itself. Now, the other argument is to say, well, it's for lightning protection. So for a proper lightning protection system, you need to put finials up, appropriately sized down conductors and big earth grids appropriate to the soil conditions. So when you've done soil resistivity tests, you can work out what would be a good value and how much metalwork you need buried in the ground. But of course, that's impractical and too expensive for a festival that's going to be there for a week, for example. So yeah, I mean, banging a rusty old nail in the ground by a few hundred mil might provide a little bit of benefit, but it's certainly by no means a solution. What you need to think about is to, well, firstly, have a look at the Plaza Lightning guidance, which I hope is going to make a bit more of an outing in this coming year as we come out of lockdown. But think about management of your electrical system. So if the thunderclouds are brewing and everyone decides to put the show on hold, think about what can be disconnected. Because if a PA delay tower gets hit, then that voltage will propagate itself all the way through the network. And if you don't need that PA tower, unplug it, create physical air gaps. Think about putting surge protection in the installation. But I hear all sorts of odd things like generators attract lightning and similar aspects. They don't attract lightning any more than a truck would, So it's important to think about the management aspects and what you're trying to achieve ultimately in trying to keep the electrical system safe. But yeah, banging in a rod is not really the answer to that. There's many more things that will be higher up the list of issues to discuss and manage. Like I say, Plaza Lightning guidance is free to download. Just need to register your details, but very much worth having a read of that if you're getting into the festival season this summer. There's lots in it as well about crowd management and similar, because often it might be safer to leave the crowd where they are than try and do an uncontrolled crowd movement out of a venue. And once you've got them out, where are you going to send them? Sit in the fields, go under the trees, hide in their cars. Those things are quite key in the crowd management planning. But yeah, finally, just quickly on bashing rods in, be aware the HSE have got quite good guidance on avoiding danger from underground services. They're quite hot on people who bash nails through underground pipes and similar. So make sure that you're aware of the content of their guidance as well, if you bash anything into the ground from tent spikes to earth electrodes. So that's that one. So if we move on, I think we onto electrical safety management now. Again, these are all myths. So should I pat test my equipment every year? Whether you're a rental company or whether it's in the office, you look at the stickers and you'll see tested in January last year, retest you January next year. Now, if we go to the next slide, for those of a certain generation, you might remember Maggie Thatcher standing at the box in Parliament going, no, no, no. And basically, it's a big no. Early guidance tried to help people understand what the risk from electrical equipment was and provided, to give people an idea about how often to check it, provided some guidance in a table. And of course, people like to follow rules and regulations, and they try and pigeonhole themselves into the industry they think they fit in that table and say, yes, I think row 5, I'm a commercial business, do it every year, right, do it every year. And don't read the rest of the book, which says, actually, these are recommended, vary it once you've decided how often stuff gets damaged. In the new edition, I've tried to kill that completely. After much debate with the committees, the table has gone. So what we've replaced it with is a risk assessment, because you need to think about who's using the kit, how often it's used, what's the environment it's used in. The extension lead under my desk here, powering the monitors and the PC, it doesn't get moved from one year to the next. There's no risk of damage to it. The quick visual inspection, no signs of overheating. It's very lightly loaded. So I'll check it once in a blue moon. But that same extension lead used in my workshop, where it's being dragged across the floor, being trodden on, and having bits of stuff dropped in it when I'm working at the workbench, for example, would need checking more often. So to say that all extension leads need checking every year is just, as you can see, clearly inappropriate. So the key driver in the new guidance is to think about, well, what risk of damage is this exposed to? And there is no right or wrong answer. No one's been prosecuted for not pat testing their kit every year, but they have been prosecuted for not having a policy and following it. So it's important that you think about your equipment, think about how you manage it, and then decide, well, what you think is reasonable. There's no one to say that what you've done is wrong. As long as you've done a considered risk assessment and thought about the risks of damage and how you manage it and factored all those in together and just come up with a reasonably argued interval. And like I say, it could be weeks or even years plus. So there's quite a lot that's changed in the guidance as well. Things like class 2 items like phone chargers, good visual inspection is probably all that's required periodically. So it's very much getting people to think a bit about what they're doing. So that's that one. So if we move on to the next one, we have electrical safety is managed by ensuring all suppliers provide PAT records for their kit. Again, very common. You go to a venue, the venue says, yeah, we want to see all your PAT records for your kit, which is great. So you present them with a lever arch file full of test records, or give them a URL to your Excel spreadsheet with all the kit, and they can cherry pick and have a look at a few items of kit. That's lovely. But then, of course, they leave you to go and put it all together. And that is where the real risk is, not really in so much the equipment itself. So if we go to the next slide, what we'll see is that having good equipment is lovely, but it doesn't stop people setting it up in a bad fashion. So I might have a perfectly lovely 63 amp extension lead running from stage to front of house, and it was tested before it arrived, all looking shiny and new, good insulation resistance, good continuity, etc. But if I route it by a door and it keeps getting chaffed and the insulation gets worn away, then it's going to present a hazard. So the checking equipment records is a very small part of the bigger picture, and it doesn't ensure any electrical safety of the temporary system that is set up. All it means is that that mixing desk at the front house position should be all right. The amplifier should be okay. The moving light in the front truss should be okay. It doesn't mean to say that in the event of a fault or damage to the equipment or the installation, that protection is going to work. And that's the reason why BS 7909 is much more about checking the installation. And so venues should be asking for verification that the system has been set up safely, not just PAT records. And part of that BS 7909 check is to make sure that kit has been checked before it arrives to site. So it's not about, electrical safety in a venue, like I say, it's not managed by checking suppliers' equipment inspection and test records solely. It's a small part of a bigger picture. So it's much more about making sure the installation is in good order. So that's that one. What's next? The next slide. Rental companies are responsible for testing kit on long tours and shows. Well, if we go to the next slide, you'll see that that is not the case, only if you've asked them to. Now, interestingly, under Regulation 6 of the Health and Safety of Work Act, rental companies are suppliers. And so they are legally bound to supply kit that is in good order with necessary instructions as appropriate for the equipment itself. And they will invariably, we hope, test that kit, make sure that it's electrically safe before it gets delivered to site, as well as functionally safe as well. So for a chain hoist, for example, you'd expect to make sure that limit switches, etc., are operating effectively. So they have that responsibility to do that, also under other legislation, including the Supply Goods and Services Act as well. The person renting the kit then takes responsibility for its maintenance, because the rental company just said, right, here's a box, 50 quid a week, thank you very much. It's down to the person who's hired the kit to manage it appropriately, erect it in a safe fashion, use it in a safe fashion, maintain it as necessary for the installation, because a rental company doesn't know that you're necessarily touring every week. It doesn't necessarily know that it's going into a long-term show. So it's the user of the kit needs to decide what they think is a reasonable interval for that inspection and testing, and discuss that with the rental company and say, look, do you mind if we do these checks on your equipment every couple of weeks? So that's how the process looks from a legal perspective. So it's very much about that communication element between rental company and hirer. But as far as the law is concerned, it's the hirer's responsibility to manage it. Now, the one exception to that, or an exception, would be leased equipment. So if you lease a vending machine or a photocopier, for example, that lease agreement might also include a maintenance agreement as well. So all you do is fill the vending machine with drinks and sweets, etc. But the company itself is responsible for coming back and doing periodic maintenance on that bit of machinery. But generally, dry hires is common in the industry. It's the hirer's responsibility to use it and manage it in a safe fashion. So that's that one. Move on to the next slide. Lampies are responsible for electrical safety. Now, this is common. We've gone to the next slide. This is common not only in theatre, but also in events, but also TV and broadcast as well. There's this kind of perception that the guys doing all the power and renting the generators are the electrical wizards on site and responsible for managing electrical safety. Well, that's not the case at all. You know, they're responsible for managing their setup. And if they very kindly provide you with a 32 amp supply to plug your audio kit into, lovely. But the audio company is responsible for managing their own electrical safety, as is the video company, as is the rigging company, because they might be using supplies provided by the lighting company. Doesn't make the lighting company responsible for their setup or their systems. Now, that management could be very simple. You know, you might run them a few beer tokens and say, can you check our kit when we put it together? They might have their own trained staff who can do basic checks and verify it themselves. But just because you happen to be the biggest user of kit on site, running all the generators and everything, doesn't make you liable. The person responsible for managing electrical safety in an event is the production, as they have that overarching duty to ensure the site is safe, and electrical hazards are just one of many. So again, just as you know, BS 7909 is my pet subject, but this is the raison d'etre behind BS 7909, which basically says, look, you know, you have a temporary system with lots of contractors providing kit, manage it, you know, and have that dialogue. There's 1,001 ways of doing it, but the key thing is that it's thought about and planned. So yeah, just because you have all the power doesn't make you responsible. Obviously, you have more duties because you've got more kit and there's more to go wrong, but that doesn't make you the one in charge for electrical safety. So next time someone says, oh, my kettle stopped working in the green room, go and fix it. That's a lovely thing to do, but you're not responsible for it just because, you know, you're the electrically skilled one who can go and fix it. So it's not the lampier's responsibility. So that's that one. So have we got another slide? Another? Yeah, right. Perennial question over cables. I hear a lot of talk about BS 7909 banning Arctic cable and SY cable, which is that cable with an armoured braid. The short answer, it doesn't. It recommends rubber cables. And if we go to the next slide, I'll explain why. The ordinary PVC cables, like Arctic blue or orange or yellow, are just ordinary plastic PVC cables. Some manufacturers put in extra plasticizer to make them more supple at low temperatures, which is lovely. You know, it means they're easier to coil up when the weather's cold, etc. But the problem with plastic cable is that if you damage it, it stays deformed and damaged. So if you've got a warm bit of Arctic blue powering a kettle in a festival concession, for example, and someone drives over it with a flight case or treads on it, when you squash the plastic, you literally squash it and it will stay squashed, whereas rubber will spring back. So plastic cable is much more susceptible to abrasion and insulation damage, which is why it's not recommended for use in outdoor environments. That's not to say you can't use it, you just need to make sure that it's got adequate mechanical protection, which could be putting in ramps, putting it out of the way, stringing it along a fence, for example, to provide or reduce the risk of mechanical damage to the cable itself. So the real Arctic cable actually is made to a peculiar British standard, which is part of that reduced low voltage 110 volt construction site system. And the reason why yellow Arctic cable can be used on construction sites, which are very arduous environments, is because of the reduced low voltage system, whereby if you touch a live conductor, you'll only get a 55 volt shock to earth. So the risk of a severe electric shock is much, much reduced by the use of our reduced low voltage. And so for that reason, plastic cables are cheaper and more readily available in that market. Interestingly, if you look at wiring regs, it says if you're using 230 volts on your building site, use rubber cable to HO7 RNF, because the rubber cable has a better mechanical protection. On the subject of SY cable, it really is designed to a German standard, not to harmonized European standards. And because it's not designed to harmonize or constructed to harmonized European standards, for a reason, no doubt, I don't know what it is, but obviously it can't comply. It means that if you're using it in an installation in the UK, as the designer, you've got to state under the wiring regulations why you think it's suitable for that use and how it meets the requirements for safety. The braiding on that cable is really there for interference suppression, and it's commonly used on machine tools and other equipment that has to move periodically for maintenance. But it's almost like flexible metal conduit is the way to think of it. So it provides that interference suppression. It's a screen for the cables going back up, and it's designed for indoor use. When you read the manufacturer's instructions, it'll say if using outdoors, particularly in temperatures less than 5 degrees, fix it permanently so it can't be bent. And I've seen countless examples of loading bays and similar where this type of cable is used. The outer clear plastic has suffered UV degradation. It's all cracked up, water's got in, the braiding is rusted, and the insulation is all getting damaged and deformed. So it's very important to make sure that it's used only in appropriate instances. On the previous slide, you saw a bit of SY with a C-form on either end. Now, C-forms don't have metal cable glands. So in theory, you need to do a pigtail off the braid, connect that to the protective conductor, because the braid must be earthed with that type of cable as well, which really lends itself to being used in metal cable glands and hence permanent installations, rather than with a plug and socket on either end. So it's very not suited for temporary events, and shouldn't be thought of as a flexible armored cable, because it isn't. That's not what it was designed to do. It is effectively just a plastic cable with a screen over the top of it. So if we go to the next slide, just a bit on rubber cables. When you look at a bit of TRS, which is the old tough rubber sheath terminology, it's now known as HO5. The HO7, HO5 RNF is the harmonized designation that's common amongst cable manufacturers, stemming from European standards. And the 07 and 05 bit relates to the voltage rating of the cable. And the reason why HO7 is chosen is because it has a higher voltage insulation rating up to 750 volts. And we don't need the higher voltage rating, but the way manufacturers achieve that higher rating is to use thicker rubber. So HO7 is specified because the jacket has got more rubber and is therefore more mechanically resilient than, let's say, an HO5 one. And if you get an opportunity, if you get a bit of HO5 2.5 mil and a bit of HO7 2.5 mil flex and look at them side by side, you'll see that the HO7 is a fatter cable with more insulation in the jacket itself. So the RNF relates to the construction of the insulation over the conductor and the insulation of the jacket itself. But the outer jacket is a synthetic polychloroprene rubber, and so it has rubber-like qualities, but it's very resistant to alkalized oils and similar, and very ideal to being trodden on and driven over and rough use in an outdoor environment. So, like I say, just to recap, BS 7909 recommends rubber cables. It doesn't ban the use of plastic cables, but just when using plastic, be very aware of the likelihood of mechanical damage. And it's very easy to see on blue Arctic extension leads where you can see the insulation's been scuffed and cut away, just being dragged across floors and sharp edges. So rubber, very much the answer for that. And also it works a lot better outside in the cold than plastic does, a lot easier to coil up at the end of the gig. So I think one more slide. Oh, just a little one I found when looking for a bit more inspiration. I found this website, RC Electrical Guy, and he had some movie myths, which I've appropriated here. But just funny things you often see on the movies, like, someone cuts a wire and you see it sparking and it dances around like a hose pipe. Of course it wouldn't. It would just sit there fizzing if it is shorting out or doing nothing. People don't burst into flames when shocked. They with a severe high voltage shock, you might smoke a bit, but usually protection works before people actually burst into flames. So that's very, very unlikely and very unlikely to happen. Murdering someone by throwing a hairdryer in the bath or similar is, again, very unlikely. I remember seeing a film years and years ago when I was younger. The guy was swimming in a swimming pool, and there was an assassin out to get him in his mansion in Hollywood. And you saw the assassin hiding in the bushes, and you saw down the barrel of his scope on his gun, and he has the crosshairs on the back of the guy in the pool, but then moves across, and he sees the underwater light, and he shoots out the underwater light. And then you see in the pool the guy apparently suffering an electric shock with flashes dancing across the top of the pool. Whereas in practice, it'll be at the same potential as a pool, swimming along going, bulb's gone again. So it's really, again, a classic myth that, you can kill someone like that. That said, people do die by touching heaters and things like that while they are in the bath because their body impedance is low. But just by chucking it in the water wouldn't necessarily have that effect. You plug in your broken vacuum cleaner or your toaster or something, and you take the main fuse out of the network. Again, the way systems are designed, that is exceptionally unlikely, and you're not going to see the whole of the town you live in shutting down just because you turn something on and it went pop. And when the power does get restored, you often see the power coming back on and all the lights in the tower block come on sequentially. Again, that wouldn't happen. They'd all just come on at the same time. So there's no sequencing that goes on. It's just there for dramatic effect, I think, is the key bit. So there you go, a couple of little funnies for there. So if we go to questions now, we've got 10 minutes for questions. Sorry, I've overrun a bit. We had some earlier. Let's have a quick look through. All right, Anonymous, what's the best way to calculate total load? So you've got a three-phase 63 amp supply. How many dimmers can you connect, assuming they wouldn't be at full? It's difficult to say. You just got to toss up how many lights you've got in the lighting rig and work out how many you'll have on at any one time and add all that up. That's the only really way you can do it. You can allow a bit of diversity. So you might have, let's say, 60 lights, for simple maths, let's say they're Parkans, 60 kilowatts, but you're not going to have them all on at the same time, even for the finale when the temptation on the desk is just to put everything on full. And you've got 40 on, then you could work off a load of 40. In the electrical design, if you overload the system, the protection will work. So, it's the risk you run of turning everything on will be that something will trip. So it's doing its job. Interested in earthing or otherwise of generators for outdoor gigs, from Ruth. That's a bit, we haven't really got time for that in this session. I have written a very good book on the subject. If you look for the practitioner's guide that's available from the IET, that's got the latest generator for earthing guidance in it. The original book I wrote was based on Code of Practice for Earthing, BS7430, but over time, it's been accepted that the guidance in that wasn't 100%. So what we've done is we've revisited this in the UK and come up with more reliable and thought through better engineered solutions to generator earthing. So when you do need to earth them, and when you don't, when you can get away without putting an electrode down, and when you do need one, etc. So it's a bit more involved than I can cover without drawing pretty pictures, I'm afraid. What periodic electrical testing is required for electric hoists and winches from Douglas? Again, depends on use. If it's a rental company, I would suggest that it's good practice, as with any rental company, to check everything either when it comes back off a job or before it goes out. If it's in your own venue and they use once in a blue moon, then test them once in a blue moon. Carry out visual inspections more often, because the damage is likely to come from, rats chewing through cables or another bit of equipment swinging across, chaffing cables or similar. So the visual inspection, regular visual inspection, is quite important. But actual electrical tests can be much reduced, because the insulation is generally quite good, and it takes quite a long time for insulation to degrade inside a box. So again, without knowing a bit more detail, it's difficult to give any definitive answer. But the key to any electrical maintenance regime, most electrical hazards can be seen with the naked eye. So a good regime of visual inspection is always high on the list of priorities. And then belt and braces testing can come a bit further down the line. What's the best equipment for RCD testing socket PEX multiple channels at once? From KB, yeah, very much a question to have offline. There are proprietary testers, but you can't test. I don't know of any test equipment that can test more than one RCD simultaneously. You have to go through them individually. Interestingly, in established guidance at the moment, there's the test you do will be to make sure it operates at its rated current, and also 5 times its rated current. Manufacturers of devices suggest that pressing the test button on its own is sufficient. So the key driver with RCDs is they're there to protect the user from an electrical fault and getting a serious electric shock. So it's accepted that the fault currents will be well in excess of the rating of the RCD. Hence, we have the slightly arbitrary 5 times test at 150 milliamps. So that is the only test really that's required. So if it trips at 5 times its rating, brilliant. They do fail. They can be more sensitive and similar. So if you have an RCD that you think is behaving erratically, then you might want to do other tests to diagnose it. But the key thing is, in the event of a fault, will it disconnect and protect the user? And that's the key driver behind some of the forthcoming discussions and guidance that are happening in sort of electrical safety circles. So that would be the prime one. Chris, why does a C-form connector have the earth closer to the cable gland as opposed to 13 amp, the 15 amp plugs, where the earth connection is further away? Just the design of the connector. Again, a bit of an urban myth there about the leaving the protective conductor wire longer in the plug, etc. There's no rhyme or reason to that. As long as the terminations are made off properly and the cable gland is nice and tight, the cable shouldn't pull out. So you don't need to take secondary action inside the plug to say, well, if the cable does get pulled out, it shouldn't, basically, in a properly looked after system and one that's constructed. So do you have a rule of thumb of the max number of switch mode power supplies or devices using them to run from a single 30 milliamp RCD? Yes, there is a rule of thumb. Anonymous, you allow 0.5 milliamp of leakage for every switch mode power supply. Now, a 30 milliamp RCD may operate anywhere over half its rating, so 15 milliamps. So in BS 7909, we recommended you take 50% of that to give yourself some headroom. So that's 7.5 milliamps worth of leakage. Because dimmers come in channels of 6, distros come in blocks of 6, and 6 is a round number that we're quite familiar with in electrical distribution. We said no more than 6 items of kit on any one distro, because 7.5 is a bit harder to work with. But if you allow, like I say, allow a milliamp of leakage for every switch mode power supply, then you won't go wrong. Often it's much less. Some systems are designed very well. A double insulated switch mode power supply that has only got the 2 conductors going in, doesn't have a protective conductor, is not going to leak current. So that doesn't matter. That can be discounted. Resistive loads like kettles or filament lamps, again, can be discounted because they don't leak current, really shouldn't, unless they're faulty. So as a rule of thumb, 0.5 milliamp of leakage per switch mode power supply. BS 7671 suggests that the standing residual current carried by a device shouldn't exceed 30% of its rating. So it's slightly more than 7909 allows, but it's horses for courses really. But 0.5 milliamp is the answer to the question. Clean Earth relates to older practices in IT of separate CPC and independent Earth, where we covered that earlier on. Any advice for dealing with festoon lighting that has 2-core cable but is wired with 3-pin C-forms? That is a very good question. There is nothing wrong with that arrangement. If it's a 2-core cable going into festoon, which is designed for the purpose, going into a C-form connector, there's no need for the protective conductor, so there's no need to connect it. So he says bravely, thinking off his head, that is not a problem. If I do think it's a problem, I'll get in touch with you. But no, there's no need to, I mean, if you did connect a protective conductor, what would you do with it? So you'd end up making an adapter for some bespoke 2-pole connector to connect the festoon light into, to then go into an ordinary disc tray, which will have an earthing contact on the socket. So no, it's fine. You can use 3-pin C-forms on 2-core cable. What about resultant electromagnetic fields for 3-phase cables? Well, if you've got an imbalance, any imbalance will be taken up by the neutral. So in an imbalanced 3-phase system, collectively around 3 phases and neutral, then there'll still be no residual magnetic field. So no issue there. Are you able to provide a simple explanation of power factor calculations for large 3-phase loads, e.g. a LED screen? No, it's not something that's easily explained without drawing pretty pictures. Very briefly, if you have a resistive load, let's say a filament lamp, as the voltage rises, the current rises, and as the voltage falls, the current falls. When you have a load with either inductance or capacitance, so generally with switch mode supplies, it tends to be slightly capacitive. The current and the voltage waveforms in the distribution are not quite on top of each other. They're slightly separated out. And so the instantaneous product of voltage times current doesn't necessarily equate to the amount of power consumed, which is why we talk about kVA and kilowatts, or VA and watts. So there is no easy rule of thumb or way of calculating it, other than lots of spreadsheets. The easiest thing is to measure typical setups. If everything is exactly the same, so if you've got 2 LED screens, both with a power factor of 0.95, they will present a power factor of 0.95. So, but when you assemble the system into a whole, they'll all be subtly different. It would depend potentially on the filtering, well, or the current draw, what each tile is presenting. So it's not a very straightforward calculation to do. So what I would suggest is just doing empirical measurements. So when you get the opportunity, put some test kit on and measure what the values are. Thank you very much. I've seen mention of electrical safety training in relation to ECS card. Can you recommend a provider? Don't know. Get in touch with me separately and I'll look into that. Phase separation. I still like all the musicians on the same phase. Sorry, Anonymous. That's just so old-fashioned. If they're liable to get a shock, then you need to sort your system out. Does audio not need to be on a separate earth? No, it doesn't. To ensure there's no earth leakage that could cause microphones to become live. No, wives' tale. Should 32 amp 3-phase sockets be protected by RCDs? In the wiring regs, it requires any socket outlet 32 amps or less to be protected by a 30 milliamp RCD. This is a bit of bone of contention because where the wiring reg stems from comes from European standards. European standards said sockets were used by unskilled, ordinary people. Where if you're using it as a distribution circuit in a temporary setup, then it's not being used by unskilled, ordinary people. So it's perfectly acceptable to risk assess the 30 milliamp RCD out. If it is powering an appliance, like a big heater or something, then yeah, put it on a 30 milliamp RCD and that should be fine. And I'm afraid, I think, probably Jamie, we've run out of time. So there's a few other questions. Again, happy to run through these if anyone wants to ping me an email. Email address, sorry, I haven't got it on the slide, it's just james@ede.uk.com. And when I get an opportunity, I'm happy to have answer any questions you might have. Regarding PoE, likely to be restrictions, guidance on types of cables, wait until it comes out. Currently, no. But that is work in progress. So the way the standards process works, it will be a couple of years before we see it embodied. So I think we're done. So, sorry, there's quite a few questions actually, but I'm afraid we've run out of time. So thank you very much for coming. I hope you've enjoyed this slightly random circular tour around different electrical safety myths and discussions. It certainly generated some other questions. So hopefully, like I say, you found it useful. Thank you for coming, and we'll see you again soon. Goodbye.